Hi, folks. Please take your seats. I just want to remind everybody we're doing the group photo at the morning coffee break, so we're going to try to keep on time as much as we can. So come on in, take a seat if you're in the hallway. Our speaker is ready, our chair is ready, and we'd like to get started.
Right. Welcome, everyone, to this bright third day of the LISA Symposium. This morning, we're going to get started with The Importance of Accurate Waveform Models for LISA by Alvin Chua.
Can you hear me? Okay, so I guess I'll just start. Yeah, so before I begin, a big thank you to the organizers of the LISA Symposium for inviting me to speak today, and also for actually having the flexibility to accommodate remote talks such as mine. Okay, so as you all know, from the first 2 days of the symposium, LISA is a space mission to observe the millihertz band of the gravitational wave sky. And this contains signals from a huge population of astrophysical sources. So in order to find and characterize any individual source in the data, LISA will need waveforms. These are essentially our predictions of the potential signals that we hope to observe. So when I say find and characterize, when I say find, I'm referring to the procedure of detection, where the data is basically compared against many waveform templates using match filtering. So match filtering is required, this technique of match filtering is required because many gravitational wave signals are actually buried deep beneath the detected noise, as depicted in the left figure over here. And match filtering then allows us to build up confidence that the signal is actually present. Now, when I say characterize, I'm referring to the procedure of inference, also known as parameter estimation or solving the inverse problem. So in the most classic example, depicted on the right here, so Einstein's equations are first used to model an astrophysical binary and to predict its gravitational wave signal, which is sort of the black curve in this middle part of the figure. And the prediction is then compared against detected data, depicted by the colored curves, in order to infer source parameters such as the binary masses, along with their associated Bayesian uncertainty. So this is the basic building block of gravitational wave astronomy that then feeds into all other downstream tasks, including the global fit, astrophysical populations. We want to do tests of GR or study cosmology. So all of these will be covered in other plenary talks today, and as well as in the rest of the symposium. Okay, so thanks to the community, we actually do have many waveform models available. Right, so Deirdre's talk right after this will go into a bit more detail on what we actually have available. So the topic of my talk, however, is simply this question: how accurate, as in accurate relative to reality, do these models need to be? So here is the short answer. I'll sort of give you a spoiler for the whole talk. For detection, they need to be reasonably accurate, right? What do I mean by reasonably? That kind of depends, right? As it always does. But the point is that many of the current models already are accurate enough, and even if they're not, there are many workarounds that are available to us. So the models need, however, to be very accurate for inference. Again, the definition of very depends on how sensitive each type of source is to its parameters, as well as the typical SNRs you might expect for such sources. And the third point is that there are some data analysis strategies that can allow individual models to be less accurate, okay? But we still actually need, unfortunately, a sufficiently good grasp of reality in order for us to refer to and to calibrate our solutions against. Okay, so here's some background that we will need for the rest of the talk. I'll try and keep it light. Okay, so these are some data analysis tools, which are pretty standard for practitioners. So the first is the familiar noise-weighted inner product on data space. That's shown in the top right here. Okay, so this is just basically, it's just the Hermitian product between the Fourier transforms of two time series, X and H, that lie in the data space. And this inner product is weighted by the power spectral density of the detector noise, right? And also it's summed over all data channels, chi, right? So in the case of LISA, there will be 3. We also need the optimal and the detection SNRs of a particular template H, right? So the optimal SNR is simply this, right? Given by this expression, whereas the detection SNR is given by the one below. So the optimal SNR is essentially, you can see, it's just the norm of the template H with respect to the above inner product. And the detection SNR is the scalar projection of the data X onto the template. We'll need the overlap, right? So here I'm using the term overlap, okay? It has, it's defined here, I define it here. Okay, it has many different names in the literature for historical reasons. It's also known as the match. Sometimes it's known as the faithfulness, but really what it is, it's this inner product, but normalized. Okay, and because it's normalized, you can thus interpret it as the cosine of the angle between two templates in the data space. There's also a related quantity called the mismatch, which is just 1 minus the overlap. Although the term mismatch has been used to mean 1 minus the fitting factor in many papers. And what's the fitting factor? The fitting factor is, if I give you some reference signal, the maximal overlap between the signal and all templates that are described by some model, that's what the fitting factor is. Okay, and so its maximal value is 1, right? And this is if and only if the signal is actually proportional to some template in the model. Okay, moving on to inference, right? So we will need the likelihood, right, of the source parameters, right? So this corresponds basically to the assumption that the detector noise is not just stationary and additive, as we assumed here, but it's also Gaussian. Okay, and here it's treated only as a function of the source parameters. Okay, and if you then, okay, so here's the likelihood, sort of given implicitly. The negative log likelihood takes this form. Okay, so I said that detector noise is Gaussian, assumed to be Gaussian, but this is actually not a Gaussian, doesn't describe Gaussian density in theta. That's because the waveform model H is actually a nonlinear function. So what we can do is we can look at the normal approximation of this likelihood, given in the usual way by the Fisher information matrix at the maximum likelihood estimate. So this is often quite useful as the Fisher matrix can be computed more quickly than the full likelihood. Okay, so how does model accuracy impact the analysis of an individual source? Okay, so the first way it does so is that it can reduce the expectation of the detection SNR and thus the statistical significance. Okay, and however, this is not anything profound. It just does so in the same way as any template that is not proportional to the signal reduces detection SNR. Okay, so if you look at this equation here, right? So the expected detection SNR for a template H true, which actually is proportional to the signal, is always greater than or equal to the maximum expected detection SNR for all templates described by any model. And this holds for all models, right? Even accurate ones. And of course, this is just a form of the Cauchy-Schwarz inequality. So if you look at the left-hand side here, it's precisely the optimal SNR of the true template, H true. Okay, and however, it's reduced by this factor. And this is precisely the fitting factor that I introduced earlier, is the fitting factor between H true and the waveform model. Okay, so the good news is that this reduction is kind of small, right, for most current models, right? In most cases, you would get a reduction by a few percent at worst. Okay. And however, there is a caveat on this statement that a few percent loss in the detection SNR is considered small, which is that actually for LISA, the search methods we'll use, as well as the significance quantification methods we'll use, are still quite open issues. Okay. But nevertheless, I think we don't have to worry too much about detection, since we also need to do inference. And models that are sufficient for inference will naturally be sufficient for detection. Right. So for detection, it's actually the computational cost of the models that can be more of an issue, because there are a very large number of templates that is needed to cover the parameter space for certain types of sources. However, there are many workarounds to this, such as using less accurate models, right, which may employ lower order approximations or have reduced harmonic content. Right. There are also semi-model sort of approaches to search, right, where both the models and the parameters that can be used are phenomenological in nature. And if the signals are loud enough, there's even the possibility of unmodeled searches, also called burst searches, where you search for simply excess power in the data. Okay, so the second and more important way that model inaccuracy impacts analysis is that it can introduce inference bias. Right? So this is to say that the inferred parameters are actually not the true parameters. Okay, and that alone isn't really a problem. It's only a problem if the inferred parameters also lie beyond the reported Bayesian uncertainty, right? Which is, in other words, the accuracy of this analysis that you're doing is actually worse than its precision, or at least its reported precision. Okay, so I'll give a quick illustration of how inference bias arises. Okay, so say we are given some true signal, H true, right? The green star here. Okay, and well, we may or may not have the true waveform model that returns H true, right, as a function of theta true. But theta true is basically what we wish to infer. These are the actual source parameters of the parameters of the source. Okay, so we may or may not have this H true model, but what we do have is an analysis model, which for now we'll assume it's inaccurate, right? Because the whole point of this talk is model accuracy. So we have an inaccurate model H, okay, and well, do we have H of theta true? Well, it's sort of indicated here, but of course we don't have access to it, right? Because we don't know theta true. That's what we're trying to infer. Okay, so what we do have, actually, given H, the true signal, H true, we can only find the closest template, call it H, of some parameters theta ml. ML stands for maximum likelihood. And we are only able to obtain that, right? Essentially, there are two ways of doing it. The most sort of thorough way, which you would want to do anyway for inference, is via sampling. Right, so sampling actually estimates the likelihood as a density over the parameter space, right? So as depicted below here, right? This black curve. Okay, but the other way, if you're after maybe a point estimate, you can just sort of do it by optimization, right? And that only allows you to obtain theta ml. Right, so theta ml by definition are these parameters such that h of theta ml, here, this red circle, minimizes the distance between the signal and the whole model, right? So you can sort of see for yourself that the closest point on the red curve is h of theta ml. Okay, so this likelihood here, right, as a density, its sharpness is essentially is the precision of inference that you can attain, right? And this is well known to be proportional to the SNR of the source of the signal. Okay, and there will be some critical SNR at which theta true, the true parameters, recall, which is what you were after, they are inconsistent with the likelihood at a given significance level, let's say 99%. Okay, and that is as depicted in this particular example. Now, if this critical value of SNR is plausible in reality for the type of source you're inferring, then it's fair to say that the model is actually not accurate enough to infer theta true. All right, and finally, we can instead use leading order approximations, right? Because sampling and optimization are computationally expensive tasks, right? So it's not easy to use them to do bulk bias studies for many different signals across the model space. Right, so we can use leading order approximations, right? So first we assume that all three waveforms here lie in sort of the same, in a region, right? Where the model, this red line, this red curve, sort of changes linearly with the parameters, right? As approximated by this line. Okay, and well, so say, okay, so this red circle, let's say you're looking at this red circle as the region, and this is essentially equivalent to assuming that you're sort of in the regime where your model errors are small and also your SNR is high. Okay, so once you make this sort of assumption, then there are ways, there are methods that allow you to sort of estimate biases much more quickly, right? Or even, sort of accuracy standards. So the first is like a linear bias estimate introduced by Cutler and Vallisneri in 2007. Okay, so essentially you sort of look at this difference vector between H true, H of theta true and H true. Okay, and then by sort of projecting it onto the tangent space here, and then pulling it back, you can sort of get a linear estimate of this difference between theta true and theta ML, right? So it's in this pictured case, it's actually a good approximation, right? Because this is a region where the waveform model is close to being linear. All right, so it's useful for bulk calculations. However, there's a caveat. It can be kind of not valid very easily, right? Once the bias gets a little bit larger. And the problem is you don't really know. Okay, so there's an even quicker and dirtier method known as indistinguishability criteria, right? And so the most common of which is this sort of 1 sigma criterion, sort of stated below. And this requires that the mismatch between the waveforms, right, sort of between any two of the three waveforms, right? But traditionally it's these two, the green star and the open circle, right? And you require that the mismatch is less than D over 2 times the optimal SNR squared, right? Where D is the dimensionality of the parameter space. Okay, so this such criteria, they're really quick, right? But they're actually the least robust because even if the linear approximation is valid, they can be a bit too conservative because of parameter correlations, as pointed out in this paper by Thompson et al. All right, so before I do a quick review sort of the work that's been done on accuracy, waveform accuracy, right, so a few more words, right? So so far, I've been focusing on waveform models, only waveform models, right? And again, waveform models describing sources that are purely using general relativity, and also these are isolated sources. Okay, however, accuracy is kind of important everywhere else in analysis, right? As you will see here, right? And over the course of the symposium, there are many parts, there are many pieces, right, that go into the whole analysis. So for example, LISA noise is not stationary and Gaussian, so we must account for, a non-stationarity and also sort of gaps and glitches in the data. Okay, that you need your response model, right? Your description of the LISA response to a gravitational wave, it needs to be accurate enough, right? So the orbits of the spacecraft need to be accurate enough to not bias inference. And also the assumptions that are used to build the time delay interferometry observables should also not bias inference. Okay, and then I use the word analysis model here, but I'm referring mainly to the set of analysis algorithms you use to sort of study the signal. Okay, and these algorithms, they are large. Most of them are stochastic in nature, so you will be susceptible to Monte Carlo errors, right? But also, these methods could also have systematic errors built in as well. Okay, and that's just for an individual source. But then the global fit, the LISA global fit, will involve many different waveform models as well as many different analysis models, right? And so errors in all of these may cross-contaminate. Okay, and finally, there's also environmental effects as well as beyond GR effects, right? So that's actually a whole other can of worms, which is beyond the scope of this talk. Okay, and for the papers I'll review, the focus is on largely on massive black hole binary mergers as well as MREs and IMREs. Okay, because these sources they're kind of the only ones where the modeling is really difficult, but also we kind of expect these sources to have very high SNR. So accuracy constraints are quite stringent. However, I'll just comment briefly here on stellar origin binary black holes, right? So these will be modeled with post-Newtonian templates, right? So one study in 2019 actually showed that, they argued that 2 or 3 PN should be enough, right, to actually infer the parameters of SOPHs without bias. However, this study was only done for circular orbits and using the very sort of crude indistinguishability criterion, right? So maybe it would be good to update it with eccentricity as well as more robust bias studies. Okay, so on to massive black hole binaries, the accuracy studies that have been done. Okay, but first a bit of background. So Deirdre will say a lot more about this in her talk, right? But for massive black hole binaries, numerical relativity simulations can be taken as essentially the truth, right? To sort of refer to and calibrate against. However, the problem is these are not template models. You can't use them in data analysis. So there are actually 3 main modeling strategies that are used by the community, right? So this sort of the 3 types of models: IMR phenom, right? Effective one body, and reduced order model surrogates, right? Which are actually just fits to numerical relativity. Okay, and these models, there's a whole ton of activity and development, right? And recent ones, basically, we've started to include sort of higher harmonic modes as well as eccentricity in the orbit, as well as spin precession. Okay, but historically, right, the development of these models, it has been motivated more by ground-based observing, and currently it still is, really. And that means that most accuracy studies that have been performed are also in that setting as well. Okay, but because LISA basically is going to be much harder, or rather, the constraints are going to be much more stringent, so we can assume that any inadequacies that show up in those studies will naturally be there, and probably even worse for LISA. Right. So one example, in this paper by Dani et al. In 2025, right? So they essentially concluded that, among the current models, the sort of cutting edge models that are used for binary black hole mergers, right? But for, in the context of, future generation ground-based detectors such as the Einstein Telescope, Cosmic Explorer, current models are basically not enough to avoid significant bias, right? And in fact, the bias can even show up for LVK, right? The LVK network at design sensitivity. And this bias, they also showed that it causes downstream bias in tasks such as measuring the Hubble parameter. Okay, so I'm running out of time. So there have been a handful of studies on MPHs in the LISA context, right? So, but mainly they focus on the bias from neglecting higher harmonics. Okay, so these studies are fairly robust, I would say, because they use combinations of not just the linear bias estimate, but also sampling and optimization. So they validated their answers. Okay, and the conclusions from this paper, Pitt et al. In 2023, is that modes, right, the spin-weighted spherical modes up to L equals to 4 are needed for unbiased inference. Okay, and then follow-up work by E et al., right, actually showed that you might need even L equals up to 6 for higher masses, spins, and inclinations, right, as sort of shown in this figure here, right, where they only analyze with 4 L equals 4. Okay, so there's also another related study on massive black hole ring downs, right? This is used for black hole spectroscopy and test of GR, right? So this one used a linear bioestimate. But the main conclusion is that they sort of worked out the number of modes that you need to include in your inference, right, in order to not have bias. So the number is about 3 to 10, depending on the parameters, but it also includes some overtone modes as well. Okay, on to MREs. right? So here, the main modeling strategy is the multi-scale self-force approach, right? And then the implementation is actually sort of done on the FEW framework, right, where we accelerate with GPUs. Okay, so in the MSF approach, right, so it sort of does contain what we can call truth, right? So this would just be in the form of higher order expansions of the evolution of these orbits, expansions in the small mass ratio parameter, right? And by higher order, I mean sort of 1 to 2 post-adiabatic order, right? So these expansions, however, are not available yet. And in the case of 2PA, they may not even be available, right, in the foreseeable future. But there's another approach where we can hybridize with post-Newtonian information, right? So this is sort of the focus of the Wasabi models. All right. Okay, one main difference between MREs and IMREs, or rather this type of modeling approach versus the modeling approaches for MPHs, is that there is an expansion. There's a decomposition, not just in terms of the angular spherical harmonics, but also in terms of the frequency overtones, essentially, right? And here, the orbit also now is more complex. It has 3 fundamental frequencies, right? And so the way that these waveforms are put together, you basically need to compute a very large number of modes, right? Thousands to even tens of thousands of them. Okay, so then the question is, how many do you need actually when you evaluate the waveform? How many do you need to not have your inference be biased? Okay, so this paper by Michael Katz and myself and others, right? It sort of indicates that actually the modes, right? Maybe you just need to keep dominant modes with 99% of the total power, and that may be enough to actually avoid bias. Okay, and then more recently, there was a study on the bias from neglecting 1PA evolution, right? So recall I said 1PA is sort of higher order evolution, which we'll need. So what happens if you neglect it? And this study was done for Schwarzschild circular orbits, right? So where the primary mass of the MRE or IMRE is not spinning, okay? But again, if you go up to 1PA, the secondary mass may be spinning. Okay, and also it was done using sampling, full sampling, right? So the conclusion mainly was that 1PA evolution is needed indeed for mass ratios that are greater than 10 to the minus 5. So this is basically saying that, yeah, it's needed for all MREs, right? And in fact, most MREs as well, right? So this is sort of confirming what we expected. There's also a study on the bias from errors in 0PA evolution, right? And so, yeah, this is essentially looking at the errors in the radiation reaction fluxes that are used to then sort of integrate the trajectories. So this study was done for Kerr circular orbits, again using sampling. The main conclusion is that, so in the flux data, we will need modes up to L equals to 30. And when we interpolate the flux data, we will need relative errors of up to 10 to the minus 6, no bigger than that, right? So this is kind of useful for the modelers. Now, finally, there's an upcoming study using sort of 2PA evolution, right? But again, in the sort of hybrid approach that I described earlier. So this 2PA terms are not really available, but we sort of borrow them from PN, post-Newtonian information. Okay, so this is a study sort of led by Josh Matthews at NUS in my group. So we are looking at Kerr-eccentric orbits now, right? Sort of the most generic space that we have available at this moment, and we use optimization to study biases. So we don't do full sampling, but we do optimize and try and find the best fit points. So we have 2 main conclusions. The first is that the fitting factors. We looked at fitting factors between 0PA models, right? So these are really the leading order models and signals which are up to 2PA. Right, and we find that actually the worst case you get is actually still a fitting factor of 0.99. Okay, and yeah, that's kind of surprising, right? So what that says is that in your 0PA model space, there will be something that resembles a 2PA signal, right? Even though 2PA evolution, it sort of diverges very quickly from 0PA, right? And the other main conclusion is that we will need 2PA information for mass ratios greater than 10 to the minus 3. So what this means is that for IMRIs, right, this is again somewhat surprising, but it indicates that for IMRIs, to actually infer, to study IMRIs and LISA data, we would need 2PA information. So this was a surprise, and thus it motivates actually more work into the hybrid approach, because it's unlikely that we'll actually be able to get the actual 2PA information. Okay, so I'm really running late. So here, right, it's just some analysis strategies, okay, which you can sort of use to reduce the accuracy requirements on waveform models. Right, so these are just some that have appeared recently. So you can do something like Bayesian model appraising.
So, Alvin, we have maybe 1 minute total, including questions. So.
Okay, sorry about that. Right. So okay, maybe then I'll just leave it here. The point is that, right. So all of these analysis strategies, right. Ultimately, you would still need an accurate model that is assumed to match reality, right? And this is needed in order to calibrate your answers against. Okay, and even this last strategy, right, where it's kind of agnostic in the sense that you expand a waveform model with some nuisance parameters, right, and then you include those nuisance parameters in the inference, in the analysis, and then marginalize over them, right? So this kind of doesn't really assume any sort of true signal model, but even in that case, even though you don't use an accurate model directly, you kind of still need it for calibration. Okay, so I'm sorry for taking up so much time. So maybe I'll just leave my summary slide up here and welcome 1 or 2 quick questions. Thank you.
All right, I guess we have maybe time for 1 question as the next speaker comes and gets set up. If any burning questions out there?
Hi there, thank you. I had a question about the EMRI accuracy analysis, that slide with the sort of heat map. And I wanted to make sure, yeah, that one. Oopsie.
This one. Okay.
I want to make sure I understand what row crit means. Is that row crit needed for detection or for parameter inference? Or tell me a little bit more about that.
Right. Sorry. Yeah. So I didn't have time to explain in detail, but yes, essentially this is for parameter inference. Basically, I think this case is the IMRI case, right? So where the signal itself is a 2PA signal, but we analyze it with 1PA model, right? So just one order below, and row crit is actually the SNR. Above which there would definitely be biases, right? And so we find that even in this case, right, where you are sort of analyzing with the best possible waveforms we would hope to have, right? But for an IMRI, it's likely that, at even modest SNRs, right, these are kind of SNRs that you might expect for heavy IMRIs, right, where the primary mass is the supermassive black hole. So these are modest SNRs, and you would expect, basically your inference is biased, right, at such SNRs already. And so that's the conclusion that we're making.
Yes, please.
Oh, thank you. I actually can't hear the chair, sorry, so I guess I'm dismissed though.
Yeah, thank you very much for that talk. And now, next up, we'll have Deirdre Shoemaker on the challenges in waveform model development for LISA.
Should be working now. Try that. This is next down. Oops, I did. Sorry.
That's all right.
And there you go.
Do you want a microphone or I stand here? I'll try to stand still.
Yeah, you can move this around.
I never stand still, so maybe this is why no one's falling off the stage.
You want the lavalier
Because you
mic?
have to, yeah.
This could be your moment.
I really like one of these mics, so you
Try that. Is that working?
Does it work? Hi,
Oh, hold
everyone.
on. I had turned it off. Now try.
Hi. Thank you. Okay. Fabulous. I won't take it too high because I'm loud. So if I get loud, let me know. Hi, everyone. Good morning. Thank you for being here. And I'm excited to tell you a little bit about waveforms in general. I'm not used to these doohickeys, so let's see if I'm successful. And so we're going to talk about some of the waveform challenges that we face as we look towards LISA. We all know this plot by heart by a Wednesday at a LISA Symposium, but I'll use it again just to point out some things. Boy, these are really big, and I don't know where to go. Okay, so when we look at slides like this, it really captures the complexity of LISA and the opportunities we have, right? Because we have all these beautiful sources from galactic binaries, both unresolved and resolved, our stellar mass black hole binary. I'll come back here and be a good girl. Is this one on now? They'll keep me honest by standing here. So, but what this picture doesn't capture is something I think Alvin just said, which is the sheer range in total mass. This is a challenge we didn't have to face in ground-based detectors, although we were surprised by the range of total mass for the black hole binaries. But these things, right, they can go from 10 to the 3 to 10 to the 7. So this is a range we haven't faced before. So it's going to be one of our challenges, not to mention that we are source limited, right, rather than always noise limited. So there's a lot of fun challenges ahead for us as we prepare. And so let's dive into not all these sources, but some of them. So here is clearly an AI-generated image. You know, it's fun to play with it. Who can resist? And this is something I stole from Steve Taylor. I don't know if he's the originator of this image, but I like it, right? So it shows you some of the differences of the waveform models that we need to generate to provide guidance through all of these sources. So we have from a massive black hole binary, our MREs that we just heard about, the galactic binaries and the stochastic, and maybe even cosmic strings, a blast from the past if you're old enough. There are a lot of amazing things that we could have it. So what are waveforms, right? So waveforms are going to be the way that we interpret what the universe is telling us, right? Just listening to the data isn't enough. We need that foreknowledge, that prediction that we have in hand to really understand what's out there. And so we can do the amazing LISA science that's possible. Unfortunately, I'm going to focus on the two ones that I think, one that I have a chance of talking about, because I don't know everything about these waveforms, but they're also the biggest challenges, I think, in preparing waveforms for the LISA mission. So I apologize for not giving a complete picture. I'll talk a little bit about the galactic binaries, but not do it justice. So everyone's seen this image probably too, because Nora's really good at creating images, so we all steal them. It's terrible. Okay, but I like this image because it shows some of the complexity of where waveforms will sit in our data analysis challenge for LISA, and to remember that it is different than ground-based detector data analysis, which you're going to hear from Tyson more later, right? So, you know, when you look at the satellites actually taking the data that's got the gravitational wave emission in it, you need this interpretive moment to actually come back and, at the end of the day, as Astrid told you about, get a catalog out so you know what's out there. So that's going to be what we're focused on today is, and Alvin did a nice job of explaining how data analysis needs to influence the waveform accuracy and efficiency, and I'll come at it from the opposite direction about how do we get the waveforms to the point where we don't contaminate the LISA science. So another famous image. So here is what I'm going to call first principle approaches to the two-body problem. So two black holes or neutron stars. Let's talk about black holes. And so there are a lot of fundamental physics approaches to how we make the predictions that turn into waveforms at the end of the day. We have, when the black holes are farther apart, a post-Minkowskian or a post-Newtonian approximation in which you make weak field and slow motion approximations to Einstein equations to solve them and produce that information. Then we have numerical relativity, where Alvin called it the truth. I like that. the truth. It's not really true, where you solve Einstein's equations directly using computational methods. And then you have gravitational self-force, where you expand the two-body dynamics and powers of the mass ratio. And we have black hole perturbation theory, which you talk about perturbed, isolated black holes, and it really gives us information about things like the quasi-normal modes. So the way these approaches are applied is when they're the most applicable. So you would use the PN information for early in-spiral, especially important for massive black hole binaries, IMRIs, which are intermediate mass ratio in-spirals, and our stellar orbit, stellar object black hole binaries. Our numeric relativity comes in when we have the late in-spiral merger in play. And our self-force would be for our IMRIs, the separate mass ratios. They're one of the beautiful signals that LISA will finally give us. And black hole perturbation theory, mostly post-merger. So you can see how all of these approaches tell us or predict pieces of the waveforms that we need in hand to do the LISA science. This slide should not be shown. It is an explanation of my ignorance about post-Newtonian and self-force. So if I were a grad student, I would not pay attention right now. But I'm not going to do it justice, so I'm going to say go read the waveform white paper because it has the depth of citations you need to walk through these approaches. And really all I wanted to show here is the amount of work and how much is being done to get us in position to maximize our science return when LISA flies. So post-Newtonian, which often confuses me, but we might not get a 5 PN order out by the time we're ready to do LISA, but nonetheless, a lot of work is happening. New approaches are coming in, things like the scattering amplitudes, and you can see, hopefully, that improvements in post-Newtonian are marching forward so that we're going to have great spin improvements, eccentricity, and things like that. Self-force community has also been making amazing strides. I mean, the community has been working hard considering they haven't had the luxury of an event like we did for the stellar mass black hole binaries, but hope is in the air. And so this is, again, another space where maybe you won't have 2PA in hand, to explain everything by the time we're ready. But you can see now really interesting work combining analytic results, pulling things from post-Newtonian, improving computational efficiency, all these places marching forward to get us the best waveforms possible when we have the science in hand. You can see probably the number one push would be to do things like getting that secondary black hole spinning, because it's unlikely that they won't be spinning in nature. So all this is work in progress. And in numeric relativity, where I'm most comfortable, I guess my wish list would be that the new codes that are being built right now that are more scalable and more efficient are ready, to get more cycles, more gravitational wave cycles, because these sources last a long time in band with the potential of high SNR, so you need all those harmonics that Alvin mentioned, and a broader range of parameters like mass ratio. A mass ratio is really the challenge for us, because that takes a lot more numerical resolution to achieve. So the challenge is really easy, right? Solve for every parameter you can think of, for longer, louder, fabulous, better, right? So there's plenty of work to go around. So if you're interested, welcome. There's lots to do. So now I'm going to move towards the source models, which Alvin already talked about. So that'll make it a little bit easier for us to move through it. Now, as I joked, right, we have the luxury for the binary black hole space that the ground-based detectors have put it through the paces. LISA's new challenges to those paces, but at least we have established a rhythm of doing the first principle approaches to predict the waveforms, and then the models reacting to that. So you have the effective one-body model. I just put the citation for the first paper. There's a million papers for all these things. Again, you can see this fabulous white paper. It only took like 5 years to write. I don't remember. 4 years to write, so read it. And effective one-body is a really interesting approach to a waveform model because it really throws in many. It's not just a hybrid of waveforms. It throws in as much physical information as available to try to produce the best waveform. So that's the effective one-body approach. The phenomenological approach, called phenom or IMR phenom, really picks a very straightforward and efficient approach, right? So this is more like building a hybrid from post-Newtonian and numerical relativity. It's fast, it maybe isn't the most accurate, but boy, you can produce those models quickly. So here's a plot showing you stitching for the phase versus the mass, the frequency and total mass in units of numerical relativity, crazy units, so of the inspiral, and then tacking on that merger and rain down from numerical relativity. And our surrogates are also something Alvin mentioned, which are an interesting approach of grabbing the numerical relativity waveforms, which are problematic because they are discrete, and turning them into a proper template space where you can interpolate between them by doing very good interpolation. So this plot is from Vijay Varma's website. If you haven't seen his website, he has some beautiful movies there showing the surrogate approach. This is mass ratio versus time, again in our weird mass units, where you grab these discrete points from numerical relativity and then you interpolate between them. So there's no approximations in addition to the interpolations. There's no additional errors coming in from making decisions about how you're going to treat the physics. But there are, of course, a lot of challenges. Again, one of them is that those first principle things aren't 100% correct. There are errors in our post-Newtonian self-force and numerical relativity that these models will inherit. And they only are as good as where we've covered in the parameter space. So you can extrapolate beyond that, but you have to do it at risk, right? So if you see models covering eccentricity of 0.8 with high spins and mass ratios, we have not run that run, right, in numerical relativity. So you have to take it with a grain of salt. Speed and computational efficiency is going to be huge as we look towards the LISA space. It's already important in the ground-based just by sheer challenge of how long these signals are, et cetera. And we've seen from Alvin, higher harmonics are going to play an important role, and I'll show you another plot about that later, because that is probably one of the things that we have to pay attention to as we plan for new models and new waveforms. This is too much fun with AI, so I'm going to apologize. I couldn't help myself. It's all wrong, so don't pay attention really, so sort of step back and look at it. But I wanted to tell a story, and I wanted to do it with images instead of words. So the point here is we've all seen this fun plot, right, where we make the point of where are we in understanding our predictions using Einstein's equations, and where are the gaps, right? And those gaps changes depending on what parameter space I'm looking at. And what's happening here, and what I think is one of the most exciting things happening in the waveform space, is each one of these fields is pushing towards the other. So for example, very early on, when the first numerical relativity simulations came out, the first thing you do is compare it to post-Newtonian, right? The early inspiral numerical relativity to the late inspiral post-Newtonian, do they agree? And you learn something about both sides. And then again, when you get to the merger of two black holes, you compare that to perturbation theory, you learn something about both. And recently, self-force has somehow miraculously been able to compare with equal mass binary black holes, despite the name of the small mass approach, small mass ratio approach. So we have seen that we actually can push each one of these boundaries towards the other and learn on either side. So I think this is where the future is going to be of getting these models ready for the LISA space. And this is where I got a little bit crazy. So I wanted to mimic the idea that what the models do is almost like a quilt on top of this, and sewing together each piece, like trying to take the best knowledge from each of these four principal areas of understanding Einstein's equations to get us where we need to be in covering the full parameter range. So if you excuse my poetic license there. So I think that that's where I'm keeping my eye on where progress is going to come in waveform modeling, is combining all these methods and taking the best of each. So then I thought we would take a quick look at a couple lessons learned from Gaussian-based detectors and one lesson from LISA. So we have been able to do a lot of work with these waveforms over the last several years since the first detection of the binary black hole. And there are differences, right? So we can't just take everything we've learned from the ground-based detectors whole. Because of course, LISA, we expect louder signals, which means, higher SNR, we expect longer, et cetera. But you can see, Alvin didn't show this plot because my student made it for his PhD, but you can see, this one told a story to me. because I think I was a little bit naive in understanding what it meant to have a high SNR signal. So this is looking at fake parameters, doesn't matter what they are, but you can see here was the low SNR attempt to use a waveform to get detection, and here is the truth, so this is the actual value of the parameters, and this is the high SNR. And so you would expect that the more SNR you have, that you would narrow in on the truth. But a waveform bias, a little error in your waveform, could actually move you off the truth as you get higher and higher SNR. So that's just one of the lessons I took away from my student. Awesome. So I wanted to share that with you. So that's one of the things we're worried about, that we'd actually move off the truth because of really loud signals when we haven't factored into our analysis approach the uncertainties in our waveforms. We also have a much broader parameter range. So this plot is from a relatively recent paper that we did. Now, this gravitational wave signal is ridiculous because it only has 5 cycles in band. So really the lesson learned there is that you cannot predict parameters when you have 5 cycles in band. But it also was an interesting lesson, I thought, in understanding sort of the limits of our waveform models and how to learn to look for those things as we move forward with better and better detectors. So this is mass ratio versus detector total mass for an injection that was like this highly massive, highly spinning black hole binary using one waveform model injected and then 3 different waveform models, where this is a subset of that model. This one's just precession, to measure the parameters. So what's the point here? The point is the models don't agree, even though they say they cover the same physics. This is not a ding on the models. They're fantastic and doing their job, but this is what it looks like when we have slight differences in how we treat the physics in each of these models, in this case, how we treat precession. And we have to learn that our waveform models aren't perfect, and either is the fundamental numeric relativity, et cetera, underneath them. Here's an example from Sophia's paper with Emanuele, looking now at LISA. So this was an SNR, the last one was an SNR of 21. This one's an SNR of 780, I think, with a 10 to the 6 solar mass binary of about Q equals 8. And here they were demonstrating in a corner plot, which are really messy and sometimes hard to read, but just looking at the differences in these circles, right, these 90% credit limits here, you can see that there's differences in how many modes you include. So I know I'm flashing up a lot of plots. It makes it hard to read. But the point here is to see that they're not all lining up, just like the previous contour plots. So when they're not all lining up, it means we're missing something. We're getting different measurements based on how we're treating the waveform model itself. So in this case, how many modes you include of those higher harmonics gave you different answers. That's what we don't want, right? We want to have one answer. We don't want our answer to depend on our decisions as we build these waveform models. So clearly, we need not only to capture all the physics, eccentricity, precession, unequal, blah, 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 but we have to have the higher harmonics when we do, which means everything has to be done in a very accurate way. So I think all these challenges I pointed out are exasperated in the massive black hole binary case by long signals and global fit. You know, that these things aren't being done one at a time. These things are all added up in a soup of sources that we have to disentangle and not contaminate the quiet memories that we're desperate to see on a loud, obnoxious binary black hole binary. I'm going to make the claim, it could be controversial, that environmental impact is not important in the BBH case, not because I don't like electromagnetic counterparts, but because it doesn't impact the waveform of a binary black hole signal, massive black hole binary. But beyond GR very well might, because if you can't disentangle GR physics, we might miss or assume a beyond GR signal that is really a systematic error. There's a lot going on in the past and in the future, so I just pointed out some of the sessions that talk about this in more detail happening at the symposium. My attempt to talk about Emery's, Neil's in the audience, so if I get in trouble, we know who to ask. So, I guess I don't know a lot. So I think these things have a really unique challenge, is that they're so long and unforgiving. I mean, 10 to the 5 cycles and bam, my God. You know, the potential if there wasn't noise is just amazing, but how do we get ready for that? So these models that we heard Alvin talk about and others are moving towards getting that generic waveform, just like for the BBH case. It's hard here because, it's hard to get not only the central mass spinning, but the secondary black hole, as far as I know, still doesn't have spin in it yet, but they're moving towards that. So, to get all this ready, we just saw from Alvin, is hard. It's not unexpectedly hard to do all that work. But there's been amazing progress. And you can see, in fact, I like this black hole perturbation toolkit, so I listed a bunch of things available because it allows you to go and see the waveforms right now, produce them for yourself, and see different ways they can be generated. Not only the most accurate possible from the 1 PA, but also looking at things like 0 PA that gives us some fast waveforms. Here I will say that I think environmental impact, of course, could be huge. So if this is sitting inside an accretion disk with so many cycles of phase error that can accumulate, clearly you do have to pay attention to what environment is producing these signals. So we heard about Wasabi a second ago. That's the self-force PN hybrid. There's also some surrogates using the self-force plus NR and then the fast I mentioned. And again, there's a ton of fun and exciting talks to happen in the past and future here, diving into the details of this challenge. I think it's going to be good. It'll be ready. I grabbed one example case to again talk about what I think is going to be the true game changer in waveform development as we look ahead to LISA, and that is these cross-cutting challenges. So I already mentioned that there was this great piece of work that connected the self-force waveforms, compared it to numerical relativity and post-Newtonian. So even at low, like q equals 1-ish, q equals 2, you could actually compare a self-force waveform and a numerical relativity waveform until you get to the merger region, which is only covered by NR, and they match really well. Like not every higher mode maybe, but the really amazing comparisons are possible. It really opens up what we can do when we're trying to cover this high mass ratio space, which is such a challenge for numerical relativity and post-Newtonian. So high mass ratio to me is like q equals 20, right? Not 10 to the 6th, like it would be for Emery's. So, that is a challenge for us. But if we can use the self-force to help build those waveforms, so now build hybrids that are self-force plus NR and model that way, it means we don't have to have 100 cycles coming from numerical relativity. We can focus on the merger, which is what no one else can predict. So I'm very excited about this. So this picture is from one of my students who is building a surrogate using the Wasabi waveform and then combining that with a hybrid that includes numerical relativity so that you can get the best of all worlds in producing these full in-spiral merger ring down waveforms with the best tools we have available right now. So I think that's very hopeful as we march forward into the future. Other sources that I won't talk about because I have no idea? No. Galactic binaries are cool. I usually ignore them because they don't need much GR, but they are amazing. We have these individual verification sources, unresolved foreground of sources, possible with the white dwarf binaries of LISA. They're mostly monochromatic, which is why I haven't included them here. However, in the way they are not monochromatic is where the interesting physics lies. How that frequency changes with time differentiates things like mass transfer and tidal interactions. So that's really where some of the really interesting physics will come out, I think, for these galactic binaries. But they're hard to model in getting all the astrophysics right, but their actual waveform morphology is not that bad. I just like cosmic strings apparently, so I put it on again. Once again, probably the best idea is to go to the waveform working paper to read about this, since I don't know much about it, but the potential's there that it's in the data, and so of course we're thinking of ways to capture it. And then this is where I'm sad that I didn't talk about it at all. All the beyond GR is huge, and that's why I'm not talking about it, because it makes my brain hurt. But it is a super active area of research, so I'm not talking about it because it's quiet, just because we don't have time. And you can see in absolutely every avenue I just talked about, we could have put the same slide and talked about where is it coming from the beyond GR side. So don't think that there isn't a lot of fun happening there. It's just overwhelming. So, and the stochastic background, I'm going to just point you to the parallel session that will talk about it with some of the techniques in science. But again, all this is described in the paper, so have at it. So we're on our way. It's not as far Maybe for some people, 10 years sounds forever, but for me, it's a blink anymore. So we really do have a lot of work to do, but I'm very, very hopeful that the work is in hand and we're going to be able to not be waveform systematic dominated when we get to the LISA science. I'm going to claim that waveforms underpin much of LISA science. It might not sound like the sexiest part, but it really is crucial to getting our science objectives met. There are different source classes. They do pose different challenges, but we can learn from each other, and so I think that's really exciting as we try to get this really broad parameter coverage of high accuracy. This probably is one of the biggest problems. The computational efficiency is going to always be a hard part. I also think as waveform modelers, we have to have a better understanding of how the waveforms are used in the data analysis, because that will impact our interpretation of accuracy and things like that. So I'm going to advocate that we pay attention to that. And it's going to require us to work together. So we're not just generating waveforms. I think that's not what we're doing. We really have to build this like ecosystem that uses each other and pays attention to the data analysis needs and really combines so that we have the best science ready when LISA flies. So thank you. I'll stop it.
We have plenty of questions.
Uh-oh. Yes, Dan?
Yeah.
Wear my polo, Neil. Be nice.
Nice to see you wearing the shirt. So, yeah, you didn't mention environmental effects, I don't think. Or maybe you did.
I did, but
Yeah. I think that's going to be more important than beyond GR, but because GR's right.
for MREs, I 100% agree with you. So MREs, environmental impact is most important. For massive black hole binaries, I don't think it's true.
Right, yeah. So, but actually, the thing I'm most worried about is computational speed of the waveforms we're actually going to use, because in a global fit, we have to do millions of iterations, right? So probably we might end up with a bit of a hybrid scheme where the analyses initially do not use the best waveforms, they use the fastest waveforms, and then maybe later we can refine, because any waveform that takes more than a millisecond to generate, we're not going to use.
Yeah.
So it has to be fast, and it might not be the best, but speed is going to be critical.
Yeah, I agree. And I think there's a little paragraph that Tyson wrote in that white paper that states that, especially for the MRE versus the blind black hole case. So I think one of the things that we have to learn to do maybe as we look ahead is the community will also get their hands on the data. And so while the people producing the catalog are going to have to make their decisions, I'm not sure how, you'd have to teach me how it's going to work when you have a global fit that you do kind of low quality, and then how do you do it? Do you do the whole thing again with high quality? Do you rely on the community to come in and put their best waveforms? Probably some combination of that will happen. So that's why I think I have to pay close attention to the data analysis crew, because even my understanding what accuracy means will change if you're taking a full year-long data set or you're doing a few minutes. Like, what does it mean to do phase in that thing? So we can't just assume it's all LIGO in our head. We really have to prepare for this. So thanks, Neil.
So maybe following or paralleling what Neil was asking, I mean, in the best sense, the whole LISA effort is a giant pyramid scheme. And there's, those of us in astrophysics are doing things that pass forward to those of you who are doing waveforms, which do things that pass forward to folks who are doing data analysis, et cetera, right? So for those of us who don't work in this, right, this seems like an enormous landscape where the things we do could influence what you all are doing in terms of waveforms. And so my real question is for those of us who are outside your community and at the interfaces of the waveform people, what should we be doing to inform how to address the biggest part of this landscape? What's the most important thing out of all this vast landscape that we should be doing to kind of help the pyramid scheme advance?
You really need to tell me if you can have that as centricity. My God, people.
Oh, that's great. That's a great example.
Really, you think your centricity is 1? Okay, where did that come from? Anyway, it just seems hard to believe when you're having emerging black holes that you could have high centricity. But for example, it's not my world, but let's grab these MREs again. I mean, as Neil said, here's where you can imagine that the environmental impact is huge, but that's also a landscape that's ginormous. So are there ways to and I'm sure people are working on that, to talk about how we approach that in the modeling world. Like, what are the classifications we can use? I said the massive black hole binaries, we don't care as much, but that's just because it takes a tremendous amount of mass to impact a binary black hole gravitational wave signal. So it's not, that's a different, it's not a modeler problem, I think, in that sense. It's more of an EM counterpart problem. But here, that's completely different because you sit there with that phase accumulating for so long. So I think it'd be nice, those are conversations where you think you need the two communities to sit together and talk. I think they are. There's a lot of work here on this environmental impact, but it is huge on both sides. We have a lot.
Thank you for a great talk and great
I'm
answers to
done.
questions.
Haha. You'll have to ask me later. Right? Is that
Great,
what
and
you're saying?
yes, yep, thank you. Great. Who's this? And so next we have interferometry testing. Yeah, from Ada.
It's a joint talk.
This-
It should be there, just hand the keynote.
So
It's all set up over here on the Mac here.
yeah,
if you're
do
comfortable.
we also have Hubert? Are they online?
And so, right, and is he's just speaking, or he's
No, I think he might want to present. I don't know.
well, we have to switch back and forth
Yeah.
then for that. But then you were going first? Or
No, here.
Okay, I misremembered that. So,
Yeah.
all right, so then we have to end this share. So there will be an online presentation first, yes?
Yes.
Okay, so then. All right, so we will switch this to online presentation. And let me just check. And so, right. So sorry about this. We need Hubert Halloin to be promoted to a panelist from the attendees. This HH. I'm sorry, I thought all your slides were together in one thing, but
I did upload it, but I don't know. He cannot switch them if his.
correct.
Yes.
But, okay, there we go. So.
Hello?
All right. Hi. Good. Okay, we see you.
I see myself too, actually.
All right, if you can
Okay.
share your slides, then we'll go ahead.
Yeah, and I'll stand
Okay,
up.
let me see. Let me see.
All right, so we see your face, but not your slides.
Here we go.
Well, not
All
yet.
right, coming
Come
up now.
on. Can you see now my slides and everything?
Looks good.
Okay.
Could we get Zoom?
Okay, so, okay, perfect.
Okay, Hubert, you can go ahead.
Okay, thank you. Thank you very much for letting us, myself and Ada, present you some actually insights on what we're going to measure on ground for testing the LISA instruments. I will start with the what we named the end-to-end test on ground, which is basically measuring and validating the performance of the metrology system as a whole on ground, and Ada is going to give a more specific talk on the signal detection and processing chain. Okay, so first let's start with end-to-end test. So, well, you all know, yeah, sorry, I have some disturbing thing here. Sorry for that. Okay, so you all know how LISA looks like, but just let's remind everybody that to measure the test mass to test mass distance between the satellites, we actually measure three things, three measurements from interferometers, from different interferometers. So one which is named the science interferometric measurements with about 10 picometers per root hertz, and two other interferometers meant to measure the distance, the position of the test mass with respect to the spacecraft, and also the reference phase between the two optical benches on the same spacecraft. So they are basically at 2 picometers per root hertz. So that's basically the level of accuracy that is required, the level of stability that is required to measure gravitational waves with LISA, and the level of performance that has to be achieved on ground for testing as well. So, yep. I lost the control, yes. So what do we measure actually? Since in an interferometer, what we measure is a phase shift that can be converted into distance fluctuation. The phase measurement resolution should be at a microcycle per root hertz, so that we can have a displacement, a noise at a picometer per root hertz level. This is done using heterodyne interferometry. What does it mean? It means that we are interfering laser beams with slightly different optical frequencies. Actually, the beat node lies within the 5 to 25 megahertz range, and this allows us to accommodate large continuous phase drifts, mostly due to the satellite movements. And also, each spacecraft can act as a phase mirror, which means that we are phase locking, or we can phase lock the local and outgoing laser from a spacecraft from the incoming beam. So basically what we record and what we have to measure very precisely is the phase fluctuation of heterodyne signals, so an electrical signal which is at between 5 and 25 megahertz range, and we need to measure the phase fluctuation of that signal at microcycle resolution noise. So this is also a standard picture that you have seen probably many times. This is globally the residual noise of a LISA instrument, and at low frequency, so let's say below a few millihertz, we are dominated by the test mass force noise, which has been tested and benefit from the heritage of LISA Pathfinder. But above a few millihertz, we are dominated by the sensing noise. And the sensing noise requires additional ground test to be validated before going to launch the instrument. So that's what we are going to talk about. So now let's focus a bit more on the end-to-end test and its main objectives. The on-ground end-to-end tests are obviously an important step of the logic of the verification of the instrument. The main objectives are basically to verify the optical metrology system's requirements. That is, this test will be applied on the engineering and qualification model of the metrology core system. And this test must be done under representative operational conditions. That is basically with representative temperature stability, of course in vacuum, and also representative of the amount of light that is received by the optical bench. This end-to-end test will also allow us to collect data that will be crucial for modeling the performance of LISA and also verify the models that we could already have. These end-to-end tests are under the CNES responsibility, so the French Space Agency here, and supported by many French labs and other partners. So what is the principle? What do we need to test the metrology system of LISA? Basically, the optical metrology system of LISA, what we are going to test is the optical bench plus a laser source and a phase meter, a representative phase meter, that needs to be put into vacuum, and then we need to simulate and stimulate the different interfaces, optical interfaces mostly, between the optical bench and the rest of the world. So that is what is represented here on this scheme. You have a simplified view of the optical bench, LISA optical bench here in the middle, just the principle of the bench, not the real actual design. And this bench with everything that needs to be extremely stable will be put in an optical vacuum tank. That is basically the optical bench plus various OGSCs, optical ground support equipments, I will talk about later. Then, in order to separate and to avoid perturbations from the electronics, we need a separate vacuum tank in which we will have the laser source itself, the phase meter, and the control units required to operate the optical bench and send the laser light. So everything here will be put in vacuum, and outside the vacuum chambers, we will have ground support equipments for the lasers, so dedicated laser sources, frequency stabilized laser sources, and a whole bench of electrical ground support equipments to perform the temperature monitoring, to supply the required voltages to all the subsystems, to distribute time with required accuracy and stability, to command control everything. So basically, in order to test this LISA equipment, we will need a lot of other GSCs to represent and to check the environment and to stimulate the optical bench. Here I have just added a few flags, meaning that we have a lot of partners. So of course, the partners we know on LISA for producing the optical bench in the UK, the phase meter in Germany, the laser from NASA, but also in France, all the ground support equipments produced and provided by labs and different labs and the CNES with partnerships with different private companies. So just let's focus a little bit on how it will look like. Here I have just represented the optical stack, which is basically the optical part of the end-to-end test, which consists of different optical systems. So in the middle, in the middle of this tower, you have basically the optical bench that will be the main system and the test. And on top of it, you have a test mass simulator that will be used, as its name states, that will be used to simulate the test mass. It's basically an extremely precise and stable steering mirror to stimulate the movement of the test mass and see the reaction of the optical bench. Then we have below the optical bench, we have what we name the beam simulator, which is actually the most sophisticated bench we have to develop, which is here to simulate the laser beams incoming and receiving the beams outgoing from the optical bench. So taking into account the fact that one beam is very weak due to the 2.5 million kilometers propagation, so it's a few hundreds of picowatts that needs to be sent to the optical bench, but we receive from the optical bench about 1 watt, 1.6 watts emitted by the optical bench. So this is a quite complex bench. It is also used to receive and send light through the backlink fiber. And of course, to link everything together, we have a stable structure that has to be extremely stable, because at the end, we want to perform picometer stability measurements between these different components. So let's make just a quick focus on the beam simulator itself. So basically, the beam simulator will be a zero-dew bench with optically contacted elements, which will be about 80 centimeters diameter. It is mostly provided by a private company, Bertin, but on which we have the different labs are providing what we name customer furnished items, basically high accuracy and high stability pointing and alignment systems that are required to align the beam simulator with respect to the optical bench. We also need to simulate the light coming from the distant spacecraft so that we have the production of what we name a flat top beam. We also need some centering mask, extremely accurate centering masks. And of course, on this optical bench, there are a lot of different photoreceivers, either single element or quadrants working at low frequency or in the bit node frequency range in the megahertz to 60 actually megahertz bit node frequency. this beam simulator also is here to provide representative optical interfaces to the optical bench. So basically in flight condition, it's 700 picowatts, so emitted by the beam simulator received by the optical bench, whereas the optical bench emits about 1.6 watts towards the beam simulator. But there is also the possibility to basically reduce the RX power to increase the RX power by 100 and decrease takes power accordingly, which allows us to basically check and reduce a lot the shot noise and chain noise and see what are the technical noise behind the dominating shot and chain noise. And why do we do such a complicated optical bench? Basically, it's to to test the performance of the scientific interferometer of the optical bench. Basically, its phase stability, to determine the TTL couplings, to calibrate the DWS, that is the digital wavefront sensing that basically gives the orientation of the beam with respect to the bench. We also want to check and verify the residual intensity noise of the takes beam. We also have to quantify and check the signal acquisition and the limits of the phase locking system. We also want to check functionally and also the performance of the clock sideband transfer, the ranging as a data transfer. And this bench will also provide some ways to verify the path length stability and more specifically to check the path length stability through the backlink or through the air, that is, so the free space versus backlink path length stability. And of course, as I stated before, all the data recorded with this beam simulator shall allow us to anchor the model, the performance model of the optical bench, and then extrapolate it to the operation in orbit. So you had an overview of the scheme and also an overview of the optical stack. Here I also give you a view of the infrastructures that are being built and designed at CNES. And you see that it's quite big. I told you about this optical vacuum tank and this electronics vacuum tank. It's a few meters diameter, 2 meters high. And the good news now is that all these facilities are being built and are built at the CNES, and also that we are building the different optical benches. And just to give you a quick status of where we are now, so the manufacturing of the optical test benches and all the facilities and GSEs required for testing LISA are being manufactured right now. We have either achieved or achieving critical design reviews for all the subsystems, and the global CDRs for the end-to-end test is scheduled basically somewhat at the end of this year. Of course, we do not started that development completely from scratch. We had a sort of prototype from, for example, the beam simulator, which was developed in the 2020s and successfully tested in 2023. And you have here a small picture of what it looked like. And this prototype was very successful since we achieved on ground with representative test equipment a stability of about 1 picometer per hertz, about above 30 millihertz, and basically better than 10 picometers, about 3 millihertz. So basically it demonstrates that we have the right technology to develop and to manufacture the optical test benches on ground. So basically all the test benches and infrastructure shall be delivered to CNES in Toulouse about early 2028 for a test campaign on the engineering model starting, let's say, mid-2028 to mid-2029, and the test on the qualification models of the metrology system from 2030 to 2031. So, as a conclusion on my part, I will say that as before, that the end-to-end tests are crucial to validating the performance of LISA before launch, but it requires sophisticated and ultra-stable benches and, of course, dedicated infrastructure. The procurement and manufacturing of all these critical items have started, and we are on schedule to start the EM testing in mid-2028. And of course, this work has been done and is being done by many partners in France and abroad, and you have here a few logos of the different partners working on it. Yeah, and
thank you.
Thank you for this present.
Yeah, thank you.
All right, so let's get you set up here. Let's see here.
Right, so we will hold questions until after Ada talks, if we have time for them.
Scroll down. There's starts from my slides. Yeah, 15.
We could have used this. All right, so now, but I need to be sharing. Oh. Can we end the sharing of Hubert? Yeah, okay.
Yes. Sorry.
Got it.
Yeah.
All right, we can do that. Yes.
Perfect.
Okay.
Thank you. So we have lots of things to talk about and not much time. So Hubert told us about how we test the whole end-to-end LISA setup, and I will just concentrate on a signal detection and processing part. So let me jump straight in. I think this is this laptop I should use. So we already all know that we measure the phase of beat node, and we know that to extract the scientific signal from the laser frequency noise and clock noise, we have to apply time delay interferometry. There's two caveats that we need to take into account, that to apply the TDI, we have to have a great knowledge of a time at which we are taking the measurement. And here is a little bit of a problem because each of our spacecraft run on separate independent clocks. So we not only have to have a high resolution timestamping of each phase measurement, but we also have to have a knowledge of what actually the clock biases and jitters are in each spacecraft. And for that, we have to exchange information about our clock through the constellation. We also have to know the absolute distance between spacecraft down to 1 meter. And I'm looking wrong laptop. And I just want to talk about the functions that we need from the signal detection chain to fulfill the main objectives for the scientific measurement. So first of all, the signal detection chain has to measure the phase shift that is being imprinted on the phase shift of the beat node. It has to provide the clock distribution between the spacecraft. It has to provide a pseudo-ranging to support the knowledge of the absolute inter-spacecraft distance. It also has to provide the inter-satellite data link. As we know, we're going to be talking only with one satellite at a time. Therefore, we have to transfer all of the scientific data to this one satellite that we can then download it to ground. We also have to provide the two key functions, which is the laser frequency control and initial beat node acquisition, where two spacecraft are going to be not vastly, but to a large extent misaligned, and we're going to have really low signal levels. So what is signal detection and processing chain? We actually already heard a lot from Ryan yesterday. This is the rendering of the units that comprise the signal detection and processing chain. It's a quadrant photoreceiver that detects light on the optical bench, interferometric processing unit, and phase meter control unit, both being the LISA phase meter units. So I want to concentrate on the three main functions of FSDPC and how we verify them. So first, the phase readout. Here is the schematic of how the science interferometer looks like. We have the combining beam splitter on the optical bench. where the RX incoming beam here red and local TX are being overlapped. We have 2 output ports of the interferometer, 4 quadrant photoreceivers in total for redundancy. Each of them, as we know from talk from Ryan yesterday, consists of diode as well as electronics that amplifies the signal. And this signal is being read by the interferometric processing unit, which consists of first the analog electronics that conditions the signal. The signal then is being digitized, and we extract the information about the phase. This then is being sent to the second phase emitter control unit that combines all of those photodiode signals into one interferometer stream and timestamps it, downsamples, and send it to platform to be ready to download to ground. And here the inside of the how the quadrant photoreceivers look like. That's the current breadboards that are being under test. Wrong laptop. So the second very important function that we have to provide and verify is the clock distribution. So what the phase meter interferometric processing unit has to do, it has to synthesize a tone that is with very good relationship to the clock that is being used as a reference for every phase point that we measure. And this is really important because this resolution directly translates how well we can later resolve the signals. And the requirement on the relationship from this signal that we send to the laser to be imprinted on light and shared with the constellation and to the clock that we use for sampling is of the order of tens of femtoseconds. So this is what we need to verify. Now this, as I said, this signal is being sent to the laser, modulated on a light and being measured on a second phase meter by the other side, which also has to meet a stringent requirement on how precisely we can track and measure this tone. And so for this, this function, we need to have 2 phase meters and verify on one hand the timing distribution and on the other hand how well we can read the tones. And the third function is the pseudo-ranging to support the accurate knowledge of the distance in our spacecraft. Phase meter has to provide pseudo-ranging. And it does that by generating a predefined pseudo-range code that is being sent to the laser, to the local laser. Then it's again being imprinted on the laser light and sent to the far spacecraft that has to track the delay of this code with respect to its local code to precision of 3 nanoseconds per root hertz. Again, this is super stringent requirement, and we need the whole chain to verify this requirement. Now, jumping straight in, how do we do that? So at AEI, we are developing test setup for verification of those 3, a few more functions, but those 3 key functions, which is called hexagon testbed. Here is the schematic of how the test setup looks like. We have the optical vacuum chamber inside sitting the hexagon bench, which is made out of zero door and optics bonded into it to provide the required optical path length stability. 6 quadrant photoreceivers sitting around. We can see here on this picture at the bottom, we have somewhere connected with a cable homemade photodiodes for the commissioning. Now they're connected to the electronics vacuum chamber, which is also thermally controlled to apply different set points of a temperature in which we measure, is seen in a picture, far picture there, far from me. And that's where the phase meter under test is going to sit into. Now, phase meter under test is connected to our laser ground support equipment to provide frequency stability, locking, and modulation for one of the lasers. The current laser preparation bench is also pictured here. So more details about the setup, preparation, and its performance is going to be tomorrow during the afternoon session by Leah Bischoff. And how do we actually measure and what the signal looks like? So we have 3 laser. So we have 3 inputs here, 3 lasers coming to this optical bench. It's hexagon since it has 6 beam splitters. And we generate pair of 3 interferometers. Now, if we add signals from all of those interferometers together, and we lived in ideal world, we will end up to 0. However, we don't, and this is exactly what we want to measure. So the epsilon shown here would correspond to the noise on one hand, our setup, our test setup, and on the other, the instruments that we want to verify. And this platform is designed to measure the noise floor of our readout system and allows us to connect up to 3 phase meters. Therefore, if we wanted to measure performance of the so phase performance, we can connect all of the channels into single phase meter, subtract the signals in post-processing, and see if we meet the performance for the single unit. But if we connect 2 or 3 phase meters and we also add a readout for the clock sidebands and PRN, we can verify if we meet performance for kind of constellation-like setup. And this is just a summary for the optical verification of signal detection processing chain. As I said, the first 3 interferometric performance to measure the noise floor of the readout system, clock sideband verification, and PRN ranging verification that includes inter-satellite data link that we imprint on the PRN code, as well as very important laser log acquisition for the very low light levels. And for this, we are developing or developed a special gram equipment that is needed to provide this measurement. And thank you. This is just the timeline of both test setups, and thank you.
I think time for one burning question, possibly, before we go take this picture. Okay, so thank you. Let's thank Ada again,
Okay,
and also Hubert.
Yeah, thank you, and sorry we ran out of time. Hello. Okay, so we're going to do the group photo now. By the way, I'm Ann Hornschmeyer from NASA Goddard Space Flight Center. Peter has had to leave, so I'm going to substitute. What we are going to do is efficiently walk straight out those doors into the sunlight and have our photo taken. And if we do it efficiently, we will have time to get back upstairs for coffee. But we do need to be back here. I believe it is 10:30. Somebody can correct me. But we need to stay on track because we have to get people onto buses to go on tours and those sorts of things. There will be box lunches later. So walk out those doors into the sunlight, down the steps, straight out.